Hello everyone, my name is Warwick. Thank you very much for joining us here today. We're going to talk to you a little bit about 3D Slicer. We've used it in our master's research, and hopefully we can, you guys can learn something from the application of this open source software. So my name is Warwick and that's Sam. I'll be going through the first section of today's presentation. And including a little bit on sort of like a workshop, and then from there we'll have a small 10-minute intermission, and Samuel will take over with the radiotherapy section for the 3D Slicer. I'd like to thank the Medical Physics Research Group, Sir Charles Gardner Hospital, and a special thank you to Benjamin and Martin for basically advertising the event for us. It's very kind of them. So let's get into it. Sam, would you like to tell everyone a little bit about yourself? There you go.
Hi, my name is Shyllon. In terms of my background, I have a Bachelor of Mechanical Engineering and a Diploma of Science, and I just recently completed my Master's of Medical Physics. I am a medical physicist at Sir Charles Gardner Hospital, Medical Technology and Physics Department, and my master's project was on the dosimetric comparison of proton therapy and cyberknife in stereotactic ablative radiotherapy treatment for liver cancer. Basically, it was a treatment plan comparison of proton and cyberknife for liver cancers. So I had to use Slicer to evaluate treatment plans. So my application of Slicer was directed towards radiotherapy, treatment plan evaluation, and comparison.
Cool. Thanks very much, Sam. And I'm Warwick, currently a scientific officer at Genesis Care, the UWA. And my project was using Slicer, 3D Slicer, to obtain three-dimensional information of different components of a CT scan, basically, and then arranging them in such a way for 3D printing. Specifically, I went into HDR brachytherapy, which is contact brachytherapy. It's close distance brachytherapy, basically. So today's goal, we hope that we can go through various different components, including how to install Slicer, just very simple modeling of Slicer as well, and various different components of what we can do in there. And as I said, we'll have that intermission period, followed by Samuel's part, where we'll go into various few other applications of Slicer. So first of all is the installation. How do we do it? It's as simple as putting in Slicer 3D or 3D Slicer into Google. It'll be your first link. So we select that one. It'll take you to a page no different to this one. And from here, we'll hit the download at the top. Again, it'll take you to another page, and depending on the type of software that you're using, the operating system, whether you're on a Mac or a Linux, you just select the stable version. Preview, I believe, is for actually creating the program source code into your computer, so you're able to manipulate certain values if that's what you choose to do. And this download will take approximately 10 minutes. It's quite a large file, so maybe have a cup of coffee and then come back when it's ready. From here, you'll open up Slicer 3D, and this is the sort of page that you will see. From here, we want to look at the different extensions that Slicer has. So these are all the different types of applications. So the way that we can look at that is going into the extensions at the top here. We will select the view function just here, which will take us into a drop-down menu similar to this, and we'll select the extension manager. So the extension manager basically these are all various different projects that other people have worked on. It's a free-to-use software, so we have a variety of different extensions, and these all give you various different tools that allow you to do whatever you need to do in Slicer. Specifically, we have radiotherapy here, and we will need to scroll down, of course. It's a little bit hidden there. And from here, we are interested in Slicer RT for our purposes. But you can see there's film dosimetry applications, gel dosimetry applications, various different other applications that Slicer 3D has. So now that we've sort of gone through the installation very quick, very easy, we'll go into the navigation of Slicer itself. So this will include just a quick run through of what you're going to view. So, okay, there we go. Oh, no, I can't see it. Give me a second, guys. So, all right. There we go. All right. So immediately you'll be introduced with a, give me a second, I'll just close that one. Immediately you'll be introduced with a scene similar to this. Now from here you have access to the different types of functions along the top here. I'm not going to go into too much detail of what each of these do. It will take way too long. Slicer is a very big tool, a very big component, and we'll do our best to run you through just the sort of general of it. So at the top here we've got add data. This allows us to pull in DICOM information if we want to. We have a DICOM database, which is an internal database for 3D Slicer. This is where you can import your various different DICOM files, which will then sort it into IDs, basically. You know, if you've got your patient ID, it'll come up here. So no, not really dissimilar to Mosaic, if anybody has worked with that. We've also got a save function, and then from here we've got modules. Now, before I was talking to you guys about that RT extension function. Now this is actually where it comes up in radiotherapy down here. So the other types of modules that you have available are all here, but then this is actually the largest variety of different tools that you have with Slicer. And some of these I will go through today, but yeah, it's quite extensive. You can sort of now start to see how much information there is here. Yeah, so where are we? Navigating Slicer itself. If I just quickly open up a file, which I will make available to everyone to download, so this will be the trial patient. It'll be available via a web link that I will distribute, perhaps when we upload the video. So I've just clicked on the patient and I'm loading that patient in, and what we have here is the CT of that patient now. From here, oh, it's still loading, sorry. Yeah. Is it going to? Should have used my computer. Yeah. So it's just thinking. So, yeah. Nothing can be helped. Might need to restart it. Yeah. Sorry, guys. Yeah. It's one of the problems is because it is open source, it's not exactly, all the bugs have not really been wrinkled out, so it's not recommended that this type of software is used for anything clinical. Yeah. This is more a kind of like a supportive tool, a way for people which don't have access to treatment planning software to be able to kind of view what's going on. Is it there? Ah, yes. This is different. Oh, yeah. That one? Yeah. I don't know how you've set yours up. Sir? Yeah. Ah. It's all good. All right. Yeah, so from here we will have our slices. I'll just quickly take those structures off. All right. So this was created in treatment planning software, the Varian treatment planning software, Eclipse, I believe it was. And what we're seeing here is no different to what you would see in the treatment planning software. You have your sagittal, your axial, and your coronal views. And through a function at the top here, just in this section here, we can change how those views are presented. So if we want to focus solely on the axial slice, we can do so by just simply clicking the red view panel. If we wanted to view, for instance, the conventional view, we can also do that. So depending on how you really want to set it up, there's a lot of sort of freedom with that. When we are with our scans, we can change the window and level of those scans as well. So we can do that by holding a mouse button and sort of dragging left to right to change the sort of brightness, and up and down changes that viewing option. So it's kind of similar to like how ImageJ, if anybody's worked with that program, it's a little bit similar to how you'd kind of do that. And with this software itself, we also have a inbuilt CT number, which represents to a single point where your mouse is. And so, for instance, if we go somewhere in the lungs, we can see there's about minus 793 there for that single point, which indicates that you're in air. The thing to note is that this is not based off your CT scanner from your department. This is Slicer's internal built CT conversion. So it's, again, not clinical. So just want to hammer that point. Yeah, so that's more or less navigating Slicer. To go through your different slices, rolling your mouse wheel, or you can adjust it through the slider bar at the top. Holding Control allows us to zoom in and out very easily. And middle mouse button allows us to move that around like so. Okay, so it's a couple of degrees of freedom there. And yes, I think we should move into the next section. So that's really rough idea. So now we're in modeling of Slicer. Whoop. And we're going to look at the volume rendering component. So this is more or less various different tools that I used in my specific research. Very useful for generating 3D structures, which can be exported to 3D printers for 3D printing. So we're going to look at a little bit of that. So we'll start with the volume rendering component. What that is a module, as shown before, and we click on the volume rendering software option. And this gives us a sort of workflow on the left. It changes our data. And what we can see here is different volumes that we can select. In this case, we want to select the CT scan. The one above RT dose is the RT prescription dose that was based from the treatment planning software. So it's actually taken that information from the treatment planning software and put it into a separate file. But in this case, we will use the CT software. And we want to generate the volume of that by clicking the I symbol. And now what we can see in our 3D view here is a block. And that's not very helpful at all. And the reason why you're seeing that is because all of the information from your CT scan is there in a 3D render. So we need to be able to sort of do a preset on that. It's taking in densities which are very low and very high. There's no gradient there. And we can shift that by sliding this bar here. And what you're sort of starting to see is your formation, your 3D render of your patient, which is lying on the table, which is very clear. Additionally, we can also select from any of these components here. For instance, if we want to look at perhaps the bone, we can focus in on the bone, and we also get a little bit of textual information there as well, which is very handy. And again, we can use the slider to take a little bit more of that information away, so we can clearly see the bone information, or we can use the slider in the back to generate more of the muscle tissue that would be present in your patient.
Is that all just from the CT?
Yeah, this is all just from the CT, yep. So raw CT data. And from here, we can also select other different various components, for instance, the CT of your fat cells. And we can, again, look at the type of different densities that are involved with those values there. So that's using those CT numbers that we were talking about earlier, which is inbuilt into the Slicer software itself. So, yeah, very interesting stuff. Now, I will go into a little bit of the cropping side of it. So we'll do bone. Just for fun. From here, we generate our sort of bone volume render, and we hit on display ROI. So ROI is your region of interest. And from here, Slicer allows us to really shape and remove components that we're not very interested in. So perhaps we want to take information solely from a spinal cord, we can remove all the other type of information that is irrelevant to us. And really, we can do that through dragging on these different slices, your axial, your sagittal, or your coronal views. We can easily do that. Or additionally, Slicer allows you to drag it through your three-dimensional model as well. And again, with your three-dimensional model here, it's really user-friendly. A simple left click and the drag, you can rotate around your model like so, or a control left click and you can rotate like so. So there's a little bit of freedom and usability there. So we can take all of this away. We'll focus really on the spinal cord at this point. Give me 2 seconds. Get it nice and very perfect. Yep, all right. And from here, we will then go into the different module, which is crop volume. And we can then select the generated region of interest, which is what we've just created then in the white box. And really simple, we can create the new volume there and just hit apply. And what this will do is it'll take all of your other information away and you're solely left with your 3D model. You've cropped down that volume to what you're after, essentially. So that is that one done. I'm going through the checklist. I will reopen this patient now, and we'll go into the next scene. Give me 2 moments. So just closed and reopened. And now I'm going to talk about the contouring aspect of 3D Slicer and how it's a little bit different to conventional treatment planning software. So treatment planning software, you'll sort of conventionally go through slice by slice, contour different regions of interest. With the inbuilt function in 3D Slicer, I think it's going to freeze again. It doesn't like it when you close it. Yeah. See, mine wouldn't do that. It's because you've been tampering around with the software. That's all right. Bear with me for a moment, guys. Yeah.
So when you crop your volume off, it's gone?
It's not gone, no. It creates a separate volume. So it copies it across. I should have shown you that. I will show you that in just a moment. Yeah. But you are able to more or less select the different volumes that you would like to be present. I'll quickly open up this patient. It's, very quick. It's a good question. Yeah. And if anyone has any questions throughout, please feel free to ask.
Calibration CT data, you said it's provided by the 3D Slicer, but you cannot use ours if you want, for example.
No.
There is no option.
Unless you get the open source software, the actual code itself, you can manipulate the code and implement your CT data set if that's what you prefer. At this point, though, there is no way to do it. There might be a extension function that allows you to do it, though. So, yes, thank you. Mine always opens up and up for, Yeah. All right. So we've got our patient again. Sorry? Python Interactor, thank you. Yep. So got our patient here again. And question from Kat earlier. It will generate a new CT data set in the form of a new series. So if we look through here on the data module, which is really easy to find, just located at the top here, we can select the series, for instance, just this one here. So it will create a separate version of this, basically, and it'll be named annotation ROI. You can change that name as well, so to avoid any confusion. Let's say you want to have many different sections, maybe of the rib cage, one of the spinal cord. You can easily do that and then label them accordingly. Yep. And with the RT dose, there's your RT dose profile, and it does actually change the corresponding value down the bottom here. So it's no longer using the CT density; it's using RT dose in the form of grey. And again, this is based on Slicer's own internal configuration. It's not necessarily a direct visual from your treatment planning software. So it will be close enough, but yeah, when you're dealing with a patient, I wouldn't recommend using the slicer because, again, you have to commission it. Yeah. Yeah, so you can see the dose there is changing. So we're at 0.8 around there, and here it's about 41. So yeah. With the contouring side of things, we want to go through our editor function. So if we know what it's called, we can click the magnifying glass here and type editor, and it will come up straight away. We select that, and this one allows us to create a label map of our segmentations, basically allowing us to do a contour of our patient. And so what you saw earlier in the data tab, all of these are the contours of the patient, which you can create yourself in terms of what we need it for. So this, again, little function here allows you to go back to a previously opened window, for instance, the editor, the contour, the segmentation. We can create similar structures like this, and I'll quickly run through how to do one of them right now for you. So I'll turn these ones off just to avoid a little bit of confusion there. And we'll just jump back into the editor function. So we select the master volume, which is our CT data. This is the volume here. The merge volume, we can use the series name. We can create a new one if that's what you want to do. It doesn't really matter. And then from here, we have various different editing tool functions that are available to us. So, for instance, the paint effect that a lot of people might be very used to. So this one really just allows us to select the region like so, and we zoom up to the next slice, do it again. Very similar to your treatment planning software. We will remove these because there's a little bit of a nicer feature to use, which is, it's a bit nicer, a little bit easier as well. And that one is actually called the threshold effect. So this is very unique to Slicer. Now, with the threshold effect, it allows us to select a threshold of our CT. So I think I just need to quickly add the structure. We'll call it tissue in this case. And what we're seeing right now is nothing. But if we slide that down, now we've created a volume effect for the entire model, which is our general tissue, for instance. So we can hit apply, and now it's created the entire segmentation for that entire model. Now, the advantage of Slicer doing it like this, you can see through just this little drop-down menu, we have various different things that it can almost auto-contour to an extent. There are limitations to this. For instance, your threshold effect, you might go too far on one scale, and it'll actually contour the entire air as well, and that's not what we want. So yeah, it takes a little bit of fine-tuning to be able to get the correct features that you're after. So you've got a variety of different ways that you can go about doing so. Bone, very, very good as well. So now we've saturated it, we might need to just quickly delete that structure. So we'll go into the bone and threshold, and then just need to find a sort of higher intensity. There it is. So yeah, it's a little bit tricky to get right. But once you do get it right, you can see that most of the bone is selected there, and then you're able to go through each individual sort of layer and remove the excess features that you're not after, basically. And so we can just hit apply, and it's more or less selected most of the bone material. And then from here, we go back into the data menu module. I'll go back into the 4-up view and quickly turn off all these other annoying contours that we've just done. I don't want them to get confused. There we go. Oh, sorry, I've jumped the gun, actually. So in the previous screen, so editor, we've selected our area, and then through here we can click Make Model Effect. Now, what this does is it generates the 3D structure. So this this make model effect creates your three-dimensional structure of what you've just really contoured. So it creates that segmentation label and combines all of those contours together to create your 3D volume. And this process might take a little bit of time. We can quickly have a look in the data. So it hasn't come up yet. Usually what will happen is it will generate the 3D model over here in this window of what you've just done. No different to what you've previously seen with these here. So these are all generated previously.
Can it handle non-uniform slice thicknesses? Sometimes what happens is series come with a 2 millimeter slice thickness. After a couple of slices, for some reason it becomes half a millimeter slice. Then the planning system sometimes say that okay, it needs to be uniform.
Yep. So it does have its internal slice thicknesses. I believe you can find that. I don't think it's in this one. Sorry, segmentations perhaps. There is a way to set that. I was looking at that earlier. Yeah. No, there is a way to do it. Was it segment editor? I wouldn't be able to remember how to do it. Sorry. Yeah. But there is that feature there. So that's that point there. So what I will do now is just, yep.
What's the difference between this function and if you go back and then there's like build and merge and build? So what's the difference between both? Because
merge and build. Yeah. So if you've got your two separate segmentations of your 3D render, basically, or your contours, if you've separated them by a couple of layers, but they're a part of the same segmentation, sometimes the software can't register that. So, for instance, a rib here, similar to the rib down here. So it will separate those two into different sort of segmentations. So the merge and build allows those two to more or less come together, and you then create your segmentation of the entire rib function, basically. Yeah. So it is useful in some aspects, especially when you're like, for instance, you're looking at the mandible with the cheekbone. There's a little bit of a difference there. So you can separate them and even put them together if you wanted to. And you would put them together if you wanted to, like, for instance, 3D print that component as one piece. Yeah. Yeah.
So what I have done is when I could use that option, so I have like two tissues. Let's say one is dense tissue and another one is like soft tissue.
Yep.
So it recreated the 3D model with different coloring. But then when I export that file into STL, so I have like two separate files.
Yes, you would.
Merging together. So I'm not sure that either I'm doing something wrong or.
Oh, if you merge those two, merge and build, and then it should create a color of just the solid structure of those two. Yeah. Those two models, yes. And then you can then export that, and I'll go into that very shortly, into your STL file, yes. So you could make just a singular print, yeah. Sorry, we had another question down the back. Yes, it is, yes, yeah. So with the Eclipse planning system, I did create three-dimensional models using this software, and I was able to export that into the treatment planning software. And a lot of the information was kept there. One of the issues was that slice thickness that Siva was just talking about. So the treatment planning software has a different slice thickness to the thickness that was defined in this software. And so what I found was my model had actually slightly lost some information in between those layers. Again, it's just configuring the slicer to be able to say, oh, this needs to match the slice thickness of your treatment planning software, and then it will line up accordingly. Yeah. Yeah, it was really cool doing that, actually, because I didn't think you could. Yeah.
One more question.
Yeah.
So it's like we use first volume rendering, right, option?
You can, yes, yeah. That's
So
just
it's
generating your
like, we use that option also
Yep.
to recreate the 3D of, all structure. And then this one is like we slice actually separate tissue. Is it like
so so these here,
yeah.
that right there is your 3D file. That's your 3D mesh,
Yeah.
essentially. What you saw before with the volume rendering is the volume rendering of just the CT scans. There is no mesh information in that at all.
Right.
So you need to contour, create your segmentation label map, and then you can export that as your 3D structure.
Okay. So
Yeah.
with volume rendering, we can't export as a STF file.
With volume rendering, no, not to my knowledge. Yeah. But using threshold methods, you can then take that volume rendering, for instance, of the entire bone, and you can export that. And from there, using other types of software, you can take away different features that you perhaps don't want, and you can then 3D print if that's your intention. Yeah. Yeah.
Because this one is a bit tricky. What images I have, that's JPEG images actually. This one is like very nice, like different intensity of images, like
Yep.
bones looks different and then the soft tissue looks different.
Yep.
What images I have, that's like very complex image because that's actually inside the breast. So that's like few images are very dark and few are good intensity. So I'm really finding pretty hard to distinguish in both. So
Have you tried using the threshold effect?
yeah.
You have? Yeah.
Yeah.
Sorry? Yeah. We can. Oh, I can show you something after. Yeah, sorry. yeah. I think Samuel has a place to go soon. So sorry, guys. All right. So we are going into the transformations model now. So for the transformations function, if we wanted to, I'll select. Let's just select the right lung for this one as an example. All right, so we've got the right lung. So the transformations, this is located again in one of the work flows, one of the modules, and it opens up a more or less a workflow like this. From here, we can apply an active transform. What that sort of means is if we look down here for your CT, where is it? Unnamed, yes, unnamed series. So I'll just move that one because that's annoying. So, it's done it already for us. Give me 2 seconds. So with this here, we can select the CT and actually shift the CT values accordingly, how we choose to, and we're able also to rotate those CT images as well. So we're not limited to just the sort of 2D slices. We can actually change the view. So if we have the scan of our patient going through like so, we are able to shift it this way and actually see the information from a diagonal method, which is very different to what you would experience in treatment planning softwares. It's an additional feature. So yeah, what you can see there is when we scroll through, we're looking at information in a diagonal plane, which I don't know if anyone's ever done before. Very cool, yeah. So you've got additional options there. You can play around with these functions. And when you are happy with this, you can simply hit the convert function here. So again, you can assign this to your CT series and create the new transformation function and hit apply. And it might take a while. I probably shouldn't have done that, sorry. But then from here, it'll come up as a displacement function down here in the field, and it will tell you what what has been displaced, for instance. And you're able to do this for various different structures as well. You can do this for your RT dose structure, and essentially what that allows you to do is you can shift your literal beam setup, almost distorting your treatment plan, and kind of do like a comparison between the two if that's something which you want to do. You know, comparing plans against almost themselves, but you've got like a similar image registration. So very interesting, yeah.
Could you save that displacement field? So for instance, like
and read it into the treatment planning software?
Yeah, you apply a set of like transformations to one particular data set, and you want to save that and then apply the exact same set of transformations to another set of data set. You can just save it and import that and apply it to...
I haven't done that. It would be very interesting to actually see if that would work, yeah. But that is not something that I've done. Yeah, and I should also note in image registration, there is an automatic tool which you can apply for two CTs. So you could have your CT of a patient which has come in 6 months, and then perhaps they've changed in that time. There is a function in 3D Slicer that allows you to merge almost on, you know, one on top of the other, do an image registration. I'd recommend looking at the YouTube tutorial on that one. I have, you know, not had the time to do it, sorry. Yeah. So lastly, the last thing I do want to talk to you guys about is the exportation of those 3D models. So we will do one of perhaps the heart, might be a good one. It's pretty small. So you can see it's not lining up to your CT scan because we've applied those transformations, but we didn't apply them to that 3D model. So the 3D model is, again, where it was at the reference point. So it looks a bit funny, but... so we want to export the heart, for instance. We hit the save function at the top here, and we're presented with basically all the types of different information that we've just either generated ourselves or have previously come in from the CT scan. All of these different information. So what we are after, it might be a little bit tricky to find it, but what we're after is the RT structure. So RT structure is here. Sorry, I don't think it's that one. Where is it? I can't see it there. Oh, that's not good. You didn't mess around with these features, did you? All right, well, yeah, with these ones, I guess you'll just have to take my word for it, sorry. But you have a save function here, and through this drop-down menu, you can locate the model of what it is called, and from here, you can select, all right, I want to save that, for instance, as your STL file, which is common 3D printing language, and that will generate the 3D model that you're after. And then from there, you can go into opening that model up in any AutoCAD software, and it'll create that mesh volume, which is what you're after. Specifically in my project, that's exactly what I was after. So, yeah, that's pretty much the final thing that I wanted to talk to you guys about. So, yeah, in this first part of our presentation, hopefully you've learned something interesting that you hadn't thought about before. And we'll go into our quick 15-minute intermission, and we'll come back in about 12:30 if that works for everyone. Yep.
Welcome everybody to the second part. I'll be talking about the radiotherapy extension of Slicer. The radiotherapy extension is one of the many extensions, as Warwick showed you guys, and this was where I spent most of my time in relation to Slicer for my project. It has a number of modules: external beam planning, beams, dose accumulation, dose comparison, segment comparison, and segment morphology. It also has an isodose, dose volume histogram, and dose volume histogram comparison module. The first couple I will present to you using the slides, and the bottom three I will show you using a demonstration, as that was what I used a lot for my project. So the starting point is always the DICOM browser, and when you load up the data the first time, you're going to have a lot of structures visible, and as Warwick showed, you will need to go through and deselect whatever you need to deselect to make the workspace more cleaner for yourself. So once you've loaded your data, then you go into the RT extension. So starting with the external beam planning and the beams, this module is used to either create your own treatment planning for research purposes. As Warwick has said, Slicer is not clinical, so generally people would use it to generate treatment plannings for research. And you can also use it to load up treatment plans that you've already created and perform some modifications, such as changing the beam angles or adding more beams to it. For my project, I desire to use Slicer, this particular module, to perform a kind of robust evaluation of proton and CyberKnife treatment plans. But Slicer in its current form is unable to load up particle therapy plans, ion plans, and it's not able to undo intensity modulated proton therapy. And I tried to work with the guys from Slicer to try and develop the source code to try and improve or add that feature to Slicer, and it turned out to be a very, very big task, and I had to leave it. But so this particular module will undo very simple 3D conformal plans. If you need to use beam shaping apertures or compensators, you can include them using the things Warwick has shown you by creating the 3D volume separately and putting it in the beam pack to try and create that model. So in terms of the workflow, it's pretty straightforward. You have the plan, selecting the plan, selecting the parameters, and then the output. And in terms of the beams, you can either edit the beam or add. When you edit the beam or add the beam, you are taken to the beam module, and this is where you can modify parameters for a specific beam. So you can do this for each of the beams. You can add as many beams as you want to create the type of dose distribution that you want to create. This process is very manual, and I guess it would be labor intensive to try and create an IMRT. I guess the best you could do is probably a step and shoot type of plan using this method. It wouldn't be very efficient though, and the fields are very limited to just square fields. And like I said, if you wanted any other type of shape, you would need to include them separately as a external 3D volume that you put in the part of the beam. I don't know if that makes sense, but yeah. So when you've generated or edited the field or the beam, when you click switch to parent plan to take you back to the external beam planning module, and you can calculate the dose distribution and see the outcome. So this particular feature is mainly for research purposes. You just need to keep that in mind. And then we have the dose accumulation module. This module allows us to either create composite dose distributions or to perform dose scaling operations. Sometimes you have metastatic tumors that are located at such distances that you need two separate plans to create the dose distribution. And this was the case for some of the patients in my project. And to allow the analysis of the dose volume histogram to be a lot easier, you can create a composite dose distribution by combining the two dose distribution into a single one. You can also use it to perform a dose scaling operation. I did this to scale the proton plans to match the same dose as the CyberKnife plans, because we found that the proton plans were consistently lower than the CyberKnife plans, to allow for a more even comparative analysis. So this is a nice feature, and the workflow is very intuitive. You have the input volume, which you use as your reference, and then you have the different dose volumes that are available in the plan, and you can combine them and select the weighting factor to create a composite dose distribution. And then you have the output, which is you can name it to whatever you want, and you get a new dose volume for which you can then analyze. And the other module is the dose comparison. This is basically just this does a gamma comparison. It has the typical things you expect for a gamma comparison: the reference, dose volume, the evaluated dose volume, the structure for which you want to compute the gamma, and the other parameters such as the distance to agreement criteria, the dose difference, and the dose values for which you don't want to calculate the gamma score. And it has a input to allow for quicker computation. This particular input will assign whatever value you put here to gamma values that are greater than this value. So if you want the computation to be faster, you would set this to a relatively low number. 2 or 3 is generally what is recommended. So in this case, any gamma value greater than 1 will be assigned a value of 1. So this will help speed up the computation. And then it has 2 options for the dose threshold or the local dose difference. So the default formula used by this particular module is the global dose difference. And sometimes you might want to use the local dose difference, which I believe uses the normalization. No, sorry, the global uses the normalization and the local does not use the normalization. So if you want to use the local dose difference, you just need to tick this button. And then the output is a dose volume with a gamma map. So it's a volume with a gamma map, not a dose volume. And to give you the pass fraction. So this can be done to generate the gamma map. And this is generally used to compare a treatment planning dose distribution versus a measured dose distribution. And then we have the segment comparison, which allows us to compare different segments. The output for this module is the Hausdorff distance and the dissimilarity matrix. The Hausdorff distance is the greatest of all the distances from a point in one structure to the closest point in the other set, and the dissimilarity matrix gives us the amount of overlap between 2 structures. The inputs are obviously the 2 structures you want to compute, and then the output is the Hausdorff distance and the matrix. The results here for an ITV and a GTV, generally you would not compare these 2 structures. I've just put it there just so you can see. When you compare a GTV with a GTV, you get obviously perfect similarities. And then we have the segment morphology. This particular module I used for my project, and it allows us to perform Boolean operations on the 3D structures, such as expanding, shrinking, creating unions, intersections, or subtracting 2 different volumes. I used this to create the uninvolved liver volume. So the liver volume subtracted from the tumor volume, and so you can calculate the dose characteristics for the LT liver tissue. I also used it so the input is the structures and the segments for which you want to perform the operations on, and you can select the different operations you want to do, and the output is going to be the new segment. So I use this also to create expansion rings about the tumor volume to try and characterize the dose gradients outside of the tumor. So this is some of the applications for this particular module. So now I'm going to go into a demonstration and show you the isodose module, dose volume histogram module, and the dose volume comparison module. Okay. Okay. So this is a proton and carbonite case that I already loaded up earlier. I have gone through and deselected the structures that I'm not interested in. So for the isodose module, you just go into the radiotherapy and then you can select it, and some the workflow for this particular module is quite intuitive and straightforward. First, you need to select the dose volume for which you want to compute the isodose distribution, and you can then select the amount of levels of the isodose. We'll stick to 5, and then you can change the gray value or the dose value for each level. The prescribed dose for this particular case was 45 gray, so we'll start with 60 just in case, and then we can change the values of the levels as we wish. You can also change the color by just double clicking on the color, and you can pick whatever color you want. We'll use blue. And then once you've done that, you can just click the generate isodose, and it doesn't take very long, and it's done. And then you can also click on to see the scales in the viewer. Just click in the scalar bar, and then you can see the values of the colors. One cool thing about Slicer is that you can link all the different views together. If you click on this link, and then you click to make the slice visible, you can see where the slice is currently in Slicer. And if you want to have the slices in the same position, if you click the shift button, then all the slices will go to the same location. Yep, which is quite cool. So shift. Yep. And the other thing to note about this module is, once you've created the isodose surface or the isodose, you can then go into the data and find it. Yep. And if you go into edit properties, you can go through and change the line thickness for each. Just to make it more presentable. Like if you're trying to generate a publication, you wouldn't want to use it at this thickness because you can't really see things clearly. And you will notice that the hotspots, so I'm not clicking them. Yeah. Sorry? The lever. Ah, yeah, sorry. Yeah, yeah. So yeah, I'll switch this off because we don't need that. Yeah. Yeah, just to make things more clearer, I will deselect the lever in data. So with Slicer, you'll find you always be going between the data module and whatever other module you're using, because anything you create will show up in the data module, and then you can make modifications in there. So that's basically the isodose module. There isn't much else to say regarding that module. You can see the hotspots more visible now. So now we're going to move into the dose volume histogram module. This is probably for me was the most useful part of the Slicer RT extension. And the workflow is quite straightforward. You have the dose you want to compute the dose volume histogram, and then you have the structures. In its current form, it will compute the dose volume histogram for all the structures. This can take quite a while, so to save time, we will just select 2 structures, the tumor volume and the uninvolved liver. And we can compute the dose volume histogram. Doesn't take long. And we can do this for the CyberKnife plan as well. Doesn't take very long. So once this is done, we can visualize the dose volume histogram data. And to make just this visible, you can click on the switch on this particular button, and it will just focus in on the data for the for the dose volume histogram. And one of the cool things about this module is we can calculate a number of the different metrics you would want to calculate for a dose volume histogram data. For example, the volume receiving 10 gray or more, and you can either calculate that volume as a percentage or as a cubic centimeter, and you can have the output here. And you can calculate some of the dose metrics as well. So you can calculate the minimum dose to this particular metric is the minimum dose in here to the 10 cubic centimeter of the volume receiving the highest doses. And you can see it's updated once you click outside. And you can also calculate the X percentage, so let's say 2%. This is pretty good. But the best thing about this for me was you can export this raw data by just clicking the export to export DVH to file. Let's click here. And you can also export the dose volume metrics as well. And in terms of the output, you end up with a Excel file with a raw dose volume histogram data. For my project, my workflow was to use Slicer to generate the CSV file, and then I created a MATLAB script to generate, to use the raw data to to do other kinds of calculations. So, yeah. And then you have the metrics as well. Yeah.
With the DVH
Yep.
data, do you know, is there a way so it's not going like every 0.2? Can you make that put like every 0.1 or something?
You can, but you have to get into the source code. Yeah. Yeah.
It's not as like terrifying as you think it is.
Yeah.
It's Python
Yeah.
integrated. So
Yeah.
if you got a background in Python or even C++, which is what Slicer was written in, which is similar to what Eclipse is written in, you'll be fine.
No, the Slicer RT was written in C++, but I think Slicer itself was Python. So one of the other cool things about, let me just go through this module and then we can discuss some of the other aspects of Slicer. So then you have the dose volume histogram comparison, which allows you to compare two different dose volume histogram data. The usefulness of this I could not find for my project, but so the workflow is you select the two dose volume histogram data tables you want to compare, and then you select the dose volume as a reference to use for the computation, and then it will give you a agreement percentage, and this is just comparing the numerical values in the tables to try and give a quantification of the similarities between the dose volume histogram data. Yeah, I haven't found an application for this yet, but probably I haven't figured out an application for that. Yeah. So this is basically, in terms of the extension for radiotherapy, in terms of the radiotherapy extension, this is the full capacity of Slicer. Some other things about Slicer is you can, pretty much everything that we've done today, Warwick and myself, you could write it up as a code. You don't have to use the user interface. You could create a code to do every aspect of what we did. So everything is completely programmable. And this is a very useful feature of Slicer for creating workflows in a clinical setting if you have some tasks that are going to be repetitive. And you can do this in the Python interactor. And there's also a MATLAB bridge in Slicer. So you can download this MATLAB bridge and use MATLAB to interact with the Slicer environment. So Slicer is very robust in that it can allow you to use Python, MATLAB, or C++. So one of the things I had to do I looked into doing during my project was to, like I said, modify the slicer source code to try and be able to implement ion plans and IMRT plans. And this is a very extensive process, and the great thing about slicer is there's a lot of help online as to how to go about this. Just to show you, this is during this process, I modified 2 of the slicer source code, and this shows you using JIT. You can see the changes you made, and the green is all the changes I made. This is all the changes I had to make to the source code for 2 of the files, just to allow it to be able to load up RT ion plans. And this is this is in C++. This is one of the coolest things about slicer is that you can do this. You can take the source code, modify it for your own application, change the formulas in there if to what you want it to do, and then you can use it for your own clinical applications, such as just workflows within the clinic. You wouldn't use it for treating patients, but you could use it for like certain workflows like image registration, other things like that. And there's a lot of support online for slicer in the wiki page and also in the community. I would recommend the community as the starting point. If you have any question about how to use any aspect of slicer, this is where you should go. The guys from slicer are very, very interested in helping you develop their program. They won't do it for you, but they'll give you all the help they can. And I've been in discussion since February with people from slicer. And this is a message that they sent me. Are you still interested? Because they care about this software becoming the best it can. So they will help you. They will do whatever they can to help you. So that is my advice to you. Any question, just ask. And within a couple of hours, somebody will get back to you. So that's basically all the things I have to share regarding the RT extension. And if you guys have any questions? Okay.
Well done, Sam and Warwick. I'm just curious, like stupid question, like when did they publish it, Slicer, and when did we start actually using it, like in B-block and stuff? So, because just a few years ago when I did my master's, we didn't have like, well, I didn't know anybody who used Slicer, I didn't know it existed, and I just realized it's much, much more intuitive and user-friendly. Like we use velocity most of the time to compare treatment plans, and this seems to be much, and it's just the fact it's open source already.
It's fantastic.
So when did they introduce it, when did we start using it?
Well, I started using it pretty much 2 years ago, at the beginning of my project. Since then, not much really has changed. A lot more extensions have become available for it. So I think one of the most recent ones is the Python Interactor. So you can open up PyCharm and basically create your code in PyCharm and have that interact with the slicer software, which is fantastic.
And do most students use it at the moment for their projects?
I think it is the intended direction. A lot of students here today are very interested in learning how the software works and what it can do perhaps for them in their research. It does give us an advantage because at the moment we don't have an educational license for the treatment planning softwares. That's freely available for us. So this gives us an extra method to be able to look into how treatment plans really work, but more importantly from individual coding of how it all works.
Yes, Slicer. Yes, Slicer.
I'm not sure when it was.
Yeah, it's been around for about a decade.
Project in 1998, and then the version 2 was released in 2007, and then version 3 a lot more later.
Yeah. Thank you. I wasn't entirely sure.
Because in our code no one uses it, and I think 1 after, and I think just 2 years ago people started using it.
Yeah, it was very, very helpful for me for what I needed to do. and
I looked into velocity. That was the first thing I tried, but it wasn't anywhere close to slicer in terms of yeah.
Now you're an expert.
Yeah.
Yeah, it's also expensive.
Yeah. Okay.
Trust me. And the other thing, I always had to go to this single workstation to do some work with slides. I could have done it anywhere at home, at uni.
Way that with velocity is expensive, you probably don't have a license to
Exactly.
yes.
And it's not as close as intuitive as
I would recommend a lot for that volume rendering stuff that you saw in the first section. It is quite intensive on your computer, as you can imagine.
Yeah.
I think Sam's computer's crashed a few times. I'm lucky I've got a nice graphics card, so I don't have to worry about it. But I do recommend having